Alright students, so in our last lab we discovered that the neuraminidase Tamiflu interaction is energetically favorable by roughly about negative 53 kcals or kilocalories per mole. Now in this video I'm going to show you the actual bioactivity level of Tamiflu as seen in the published literature, and then I'm going to show you how to modify the Tamiflu molecule in whatever way you choose and determine if your new structure that you've made is more or less favorable than the original Tamiflu. The objective, of course, is for you, my students, to be able to see if you can invent a drug that, at least on a computer page and calculatedly, has a more favorable interaction with the neuraminidase and therefore may be a more potent drug. This type of approach, incidentally, is one of the ways in which pharmaceutical companies design drugs, beginning with drug leads and gradually modifying them until they come up with things that, on a computer at least, are calculated to show more favorable interactions with the enzyme. So to do that, I'm going to begin by taking you to a magical peer-reviewed publication. This one comes from the Journal of the American Chemical Society, or JAMChemSoc, commonly called JACS by chemists, from 1997, volume 119, pages 681 through 690. This is the paper in which these researchers reported the synthesis and bioactivity study of the molecule that would eventually be known as Tamiflu. We're going to go ahead and zoom down to page 5. As we go to page 5, you'll notice that they report the synthetic steps that they used to assemble the actual molecule, and then they show the molecule itself, as well as various analogs. Please note this group right here that says R. That R group was varied from one analog to the next, and the resulting analogs were measured for their IC50 values, which I'll explain momentarily. This table, table 1, shows the variants that were made. For example, they made an analog that had a hydrogen here in the place of R. They made an analog that had a CH3 or methyl group in the place of R. They made another one that had an ethyl group, and so on and so forth. They then ran a bioactivity study in order to measure the IC50 value. Now, an IC50 value, just so you know, is the maximal inhibitory concentration value. What that means is this is the concentration of a compound that is needed in order to inhibit the viral activity of this neuraminidase virus in this case by 50%. What does that mean? Well, what it means is that the smaller the number here, the more potent the molecule is. For example, this molecule right here that has a hydrogen in the place of R has an IC50 value of 6,300 nanomolar, which means that you have to achieve a tissue concentration of 6,300 nanomoles per liter around the virally infected area in order for the virus's activity to be inhibited by 50%. As you go down here, you'll notice that one of the isomers, this isomer 6H, has an IC50 value of 1 nanomolar. That is very, very potent. This isomer 6H has an isopentyl group attached at position R and, as you might have guessed, is indeed the structure of Tamiflu. So here's what we're going to do. We'll begin, as I discussed earlier, by opening up our DS Viewer Pro software by clicking this icon. We of course click the OK button here just to ignore it and open up the software. We'll now click Open, and we'll open up our 2HU4 10,000 min file as we've done before, and then we'll navigate using the rotation tool around in order to see if we can find Tamiflu. Tamiflu is of course the molecule that's adjacent to this positive 1 charge. It's kind of difficult to find, but it's in there. If we double click on it right there, it brings it right out. Now, because once again we only want to pay attention to the active site region that's most significant immediately around the Tamiflu, and we don't really need to look at the periphery so much because its conformation does not change significantly during the drying minimization, we'll go ahead and select the molecule as we've done here, and then click Edit, Select, and choose Group, Active Site 8A. We type Select and then hit Close. That's all selected. We now copy it. We'll click New to open up a new document, and then we'll hit Paste. We'd click out here in the canvas, and we now have our Tamiflu molecule and just the business section of our active site. Now what we want to do is modify our Tamiflu, so we're going to double click on it right here, click on View, and select Show Only. We'll now click this black square box to make Tamiflu bigger. You'll notice that the isopentyl group that I mentioned before is this one kind of over in this region. We'd like to select it and now change it. So we're going to grab the selection tool up here, kind of scroll around here and delete this. So if you select this branch here and push the delete key on your keyboard, it will remove it. And then we'll remove this branch here by doing the same thing. Now I'm just kind of curious, I would like to change this carbon atom right here to a hydrogen because I would like to look at the analog that has a hydrogen here attached to this oxygen as opposed to an isopentyl group. As we noticed in the paper earlier, the hydrogen analog had a much lower potency as a medicine. So we'll go ahead and select this and type the letter H on our keyboard. That will now give us a hydrogen at this position. We'll now go ahead and go back to View, Show All, and click this black box right here to zoom out. We now have our Tamiflu, our new modified Tamiflu that isn't actually Tamiflu anymore. It has a hydrogen at this oxygen position, so it's got an OH right here. We now want to energy minimize this new analog of Tamiflu that we've just made. So I'll go ahead and double click on it to select it, and now I'll go up here to Modify, Drying Minimize. I'll select 1000 iterations and make sure to check all 3 boxes here, and then select OK. The molecule's conformation has now been moved around to attain the most energetically favorable conformation available. At this point, we now need to obtain the energy level for the enzyme-substrate complex, that is the energy level for this enzyme active site interacting with our substrate, this modified Tamiflu. And then we'll afterward obtain the individual energy levels for each of them independent from each other. To do this, we want to select our modified Tamiflu molecule, cut it out, and then select Paste to put it back in. This once again tells the software that these 2 molecules, the enzyme active site and the modified Tamiflu, are indeed separate and independent and should be evaluated in that way. We'll now go to Modify and select Drying Minimize. We'll select now 0 iterations and make sure to check this box that says Include Intermolecular Forces. Having this box checked, of course, ensures that the software will include all of the favorable and unfavorable intermolecular interactions between the modified Tamiflu and the enzyme, so that the final energy that we calculate will be the energy total of the enzyme substrate complex. Go ahead and select OK. The minimization is now done. To see the results, we'll go to Window, New Data Table. We now click the Molecule tab, and notice up here that the final drying energy levels are 501.58 for the enzyme and 8.49 for the substrate. If we add those together, that gives us the total energy level for the enzyme substrate complex. That number comes to 510.07. Now we need to obtain the energy level for the modified Tamiflu itself and the enzyme itself independent from one another. Let's go over here to our original window by clicking Window and going back to our Molecule 2.1. We'll now go ahead and go to Modify, Drying Minimize, except this time we'll deselect this box that says Include Intermolecular Forces. This way it will not include the interactions between our modified Tamiflu and the enzyme. So the energy levels it spits out will be the individual energy levels of each of those substances independent from each other. We now select OK. Now to see those numbers, we'll go ahead back up here to Window and select New Data Table. We click the Molecule tab and look at these numbers. The numbers are, of course, 527.84 for the energy level of the enzyme itself and 25.74 for the modified Tamiflu. In order then to obtain the total delta E here, we need to use the equation that I showed you before. Delta E is going to be equal to the energy level of the enzyme substrate complex minus the sum of the energy levels of the enzyme and the substrate independent from each other. So to calculate that then, I take my 510.07 and subtract from it the sum of 527.84 and 25.74. That final number comes to negative 43.51 kilocalories per mole. You'll notice that this number is not as negative as the delta E for the original Tamiflu itself. Because it's not as negative, that means that this substrate, or this modified Tamiflu, is not as energetically favorable and is therefore not as good of a potential medicinal candidate as the original Tamiflu. Your assignment for the rest of this lab is to continue double-clicking on this, going to View, Show Only, and then modifying the structure of this Tamiflu, and then repeating the same process, the drying minimization, and calculating the new delta E for each of your new molecules that you made until you find one that has a more negative delta E than the original Tamiflu. In other words, you're trying to obtain a structural analog that is more energetically favorable and therefore possibly a better potential medicine than the original Tamiflu. For you, my students, then, the assignment after you do that is to make a table of some sort in which you show the various analog structures that you guys made and the overall final delta E that you obtained for each of them. Now, if you want, you can refer back to the table I showed you in the original Jack's article earlier in this video as a guide to help you look at possible specific modifications you guys want to make on that oxygen, or you could try other modifications elsewhere in the molecule. One thing that might be interesting is that if you guys are successful in designing a molecule that is much more potent on a computer than the original Tamiflu, we might actually end up using it as a synthesis project in my research lab. If we end up discovering a new medicine that's even more active than the original one, we could patent it and, market it and stuff, and then use the money to, pay for scholarships for students or ice cream or something. Anyway, so that's basically the end, and that is your assignment. I'll leave it up to you to finish it. Please feel free to contact me in the meantime if you have any questions. Until next time, students, have an enjoyable and wonderful rest of your day.